Hello, this video covers the lecture part of Lab 7 and 8, which are about the introduction to sequential design and flip-flops. We're going to start first by introducing what a sequential design is. Then we're going to move on to the definition of a digital clock. Next, we're going to introduce Lab 7, which is about flip-flops. And finally, we're going to do an exercise for Lab 8, which is one application for sequential design, which is the 2-bit incrementing counter. Up to last lab, we've been only dealing with combinational circuits. In combinational circuit, the output depends solely on the current inputs. So it's a combination of inputs and outputs. So examples of a combinational circuit include an AND gate, XOR gate, multiplexers, or a combination of those. In sequential circuits, the output depends on the current input as well as previous inputs. So there is a concept of sequence here. Usually with sequential circuits, the circuit requires the use of a sequential element, such as flip-flops, which we're going to introduce in this video. In order for sequential circuits to have a concept of sequence or time, a digital clock is necessary. Basically, a digital clock is a signal that alternates between 0 and 1 with a specified frequency. For example, we can say that the circuit component updates their value at the rising edge of the clock. The rising edge of the clock basically is the transition of a clock between 0 and 1, or from low to high. Alternatively, we can say that the elements of the circuit or the components update their value with the falling edge of the clock. The falling edge of the clock is the transition of a clock from high to low or from 1 to 0. One of the basic building blocks of a sequential design is the flip-flop. An example of a synchronous flip-flop includes the D flip-flop, the T flip-flop, the SR flip-flop, and the GK flip-flop. When we say a flip-flop is synchronous, it simply means that the output of the flip-flop updates its value with the clock. We could say with the rising edge of the clock, for example. Here you see a figure of a D flip-flop. As you can see, it has one input, which is the D, and it takes the clock as well as an input, and it outputs Q and the inverse of Q. The D flip-flop or the theta flip-flop is the simplest type of flip-flops. The output of a D flip-flop changes its value to match that of D, but it only updates its value with the clock. So we can say that the next value of Q, or Q next, is equal to D. Notice that Q and Q next are the exact same signal, except that Q next is the new value of Q, so at the next clock edge. So simply put, we can say that with a D flip-flop, the value of Q next is equal to D. With the T flip-flop, the value of Q next either stays the same or it toggles its current value depending on the value of T. From its name, a T flip-flop is a toggle flip-flop. If the value of T is 0, then Q next remains the same as Q without any changes. If the value of T is 1, then Q next will be Q bar. That means whatever value Q was, it will flip, or you will output its complement, and so on. An SR flip-flop or a set-reset flip-flop is different. It takes two inputs, S, short for set, and R, which is short for reset. That means if both S and R are 0, it means we're not setting, we're not resetting. That means Q next is going to stay the same without any changes. if the value of set is 0, means we're not setting, and the value of R is 1, means we are actually resetting, then Q next is going to change to 0. So it means reset to 0. In the third combination, here we have the value of S or set is equal to 1, means we're setting, and the value of R is equal to 0, it means we're not resetting. So that means set the output to 1. So the next value of Q is going to be 1. In the last combination, we're trying to both set and reset at the same times. That's why this option is not allowed by the SR flip-flop, because there is some sort of contradictory here, or a contradiction here actually. Alternatively, you can restate or redraw the state table of the characteristic table of an SR flip-flop, so that you can say Q next is equal to Q. That means there's no changes at all if S and R are both 0. If R is 1, S is 0, means reset, so the output is going to be 0 regardless of the previous output. If set is 1, R is 0, it means set to 1, so the output is going to become 1. If both set and reset are 1, then this option is not allowed. Someone named Jack Kelby made some improvement on the SR flip-flop and renamed it so that it became the JK flip-flop. So basically with the JK flip-flop, you can say that J is actually equals to S in the SR flip-flop. So J means set or S, K means reset or R in the SR flip-flop. Except in the last two options, instead of having them not allowed, just like the SR flip-flop, with the JK flip-flop, if both set and reset are active, what you're gonna do is toggle the output. So Q next is gonna be Q bar. Here you have Q is equal to 0. That means Q next is gonna become 1. And in the last option, Q is 1. So when we toggle it, it becomes 0. So remember, a JK flip-flop is exactly like the SR flip-flop, except when you have the options or when you have the combination J and K are equal to 1, then this option is no longer not allowed, but rather you will toggle the output. So if it's currently 1, we're going to change it to 0 in the next cycle, and so on. In Lab 1 Experiment 1, you're required to connect the JK flip-flop in Logisim and verify the JK flip-flop behavior. So here I have a screenshot of Logisim with the Experiment 1 circuit connected. Just a few important notice. To find or to place a JK flip-flop in Logisim, you need to expand the memory folder or the memory group first, and then choose JK. Here you'll also find all the types of flip-flops you'll need for this lab. Notice that I've connected input pins for J, K, and the clock, and for the output Q, I've connected an output pin. In experiment 2 of this lab, we're required to convert the JK flip-flop in Logisim so that it operates as a D flip-flop. That means we have the JK flip-flop circuit here, and our goal is to create some small circuit here and attach it to the JK flip-flop so that it works as a D flip-flop as a whole. Here we have the characteristic table of a D flip-flop as well as the characteristic table of a JK flip-flop. So our goal is to modify the JK flip-flop or build on it a small circuit so that it will act as a D flip-flop. So let's do some exercise to help us reach our goal, which is the completion or the converting of a JK flip-flop so that it acts as a D flip-flop. The exercise requires us to find the input combinations of J and K that will result in the values of Q next in this table. So here we have Q and Q next changing between 0 and 0. So we need to look up from the JK characteristic table this case. So here we have 0 to 0. In the table there's two cases that will make sure we have this output combination or output sequence. So for that we're going to copy the values of J and K that will result in this sequence at the output to happen. So we have two cases, 0, 0 and 0, 1. So we're going to copy these values and put them in the table. In the next case, we have the transition from 1 to 0 for Q and Q next. From the table again, we found out that in order for this transition to happen, we need the values for J and K to be either 0, 1 or 1, 1. So we're simply copying these values in the table that we have. In the next case, we have the transition of Q from 0 to 1, and for that to happen, we need the values of J and K to be 1, 0 or 1, 1. So we're going to copy these and put them in the table here. Finally, in order for the transition between Q equal to 1 to Q next equals to 1, so there's no change. So in order for this to happen, we need the values of J and K to be either 0, 0 or 1, 0. So we're going to copy these values in the table here. Notice that in some cases, like here, J is always 0 no matter what, right? Whereas K could be either 0 or 1. So you can say that instead of K being 0 or 1, you can say it's don't care, right? So we can replace that with an X. An X in digital logic means don't care. Then J has to be 0, so we can replace these two zeros with just one single 0. We're going to do that with the rest of the table. So this will result in having this final table here. We'll use this table to complete this exercise. What you see here on the right hand side is the table that we've derived when we did the exercise. On the left side of the screen you see the D flip-flop characteristic table. So what we're going to do next is, knowing the characteristic formula or equation for a D flip-flop, which is Q next is equal to D, we're going to add an additional column on the left hand side of the table so that it will be named D. And then, knowing that D is equal to Q next, we're going to copy the value of Q next here. So here is going to be 0 and then 0, 1, 1. Just like that. Now with the help of this table, the next step is to create K-maps for each of J and K. We're going to start with the K-map of J. It's going to be a 2 by 2 K-map, and inside of it we're going to copy the values of J. We're going to start with 0, don't care, and then 1, don't care. Next, we can group the ones that we have. This will result in this one being grouped with this x. Finally, we can figure out that J is equal to D. Next is creating a K-map for K. Again, it's also going to be a 2x2 K-map, and inside of it, we're going to have don't care 1, don't care 0. We can group this one with this don't care, and that will result in the expression K is equal to D bar. Now, knowing the Boolean expressions for each of J and K, we can simply create the circuit diagram that needs to be attached to the JK flip-flop so that it will act or operate as the D flip-flop. So this is the JK flip-flop. Now we're going to alternate J so that it becomes exactly equal to D, and K should be D bar, so that means we're going to need to connect an inverter in there and then output the result. So now this JK flip-flop, after this modification, will act as a D flip-flop. Now we're going to move on to experiment 3 of this lab, which requires us to design a 2-bit incrementing counter using JK flip-flops and to test it using Logician. First, we're going to list the steps necessary to design a sequence generator. If you're interested in reading them, you can pause the video and read them, but we're going to explain them one at a time when we do the solution of this experiment. So in order to design the 2-bit incrementing counter, we're going to start with the first step, which is to draw the state diagram. State diagram basically consists of circles, and inside their circle, we're going to state the state name and the output. For the purpose of this lab, we're going to only state the output of that state. So starting with the first state, since it's a 2-bit incrementing counter, we're going to start with 0, 0. In the next state, we have 0, 1. Notice that we're just incrementing. So from 0 transitioning to 1. The next state will be 1, 0. Then we have 1, 1. So that's the last state in our 2-bit incrementing counter. But since this is a counter circuit, then just like with any counters, you always reset back to 0 if you reach the last state. The next step is to count the number of states. Here we have a total of 4 states. So that means we're going to need log base 2 of 4, which is 2 flip-flops. So step 2 only helps us find out how many flip-flops are necessary to implement the circuit. Now in step 4, we're converting the state diagram we've generated previously into a state table showing Q and Q next for every flip-flop. We've determined that we're going to need to use 2 flip-flops. You can name them FF0 and FF1. So that means in the table we're going to need 1 column for Q1, 1 column for Q0, 1 column for Q1 next, and Q0 next. And now from the state diagram, we're going to complete the table according to the current state and the next state. So if the current state is 0, 0, then the next state would be 0, 1. Next, if the current state is 0, 1, then the next state is going to be 1, 0. Thirdly, if the current state is 1, 0, then the next state is going to be 1, 1. Finally, if the current state is 1, 1, then the next state is going to be 0, 0 again. In step 5, we're going to complete the state table with the input combinations for J and K that will result in Q changing to the value of Q next with the help of the cheat sheet or the table that we've generated earlier on the right hand side. We're going to start with Q1 next, and determine J1 and K1 that will help us reach Q1 next given Q1. We're going to start with these because notice that they all belong to flip-flop number 1. So let's examine the first case here. Q1 starts at 0 and then it changes to 0, or it stays at 0, so there is no change. So in order for Q and QNX to have this transition to happen, then the values of J and K must be 0 and don't care. So we're going to copy J and K values in the table as J1 and K1. In the next case, we have Q1 transitioning from 0 to 1. So we're going to look up from the table the values of J and K that will give us this transition. And it turns out to be 1 and X. So we're going to copy the values 1 and X for J1 and K1. As such. In the next row, we have Q1 transitioning from 1 to 1. So in order for this to happen, we need the values of J and K to be don't care and 0. Finally, from 1 to 0, we need J and K to be don't care and 1. We're going to complete the same thing we did for flip-flop number 1, but this time we're going to do it with flip-flop number 0. So now we're going to look at the green signals here. Q0, Q0 next, J0, and K0 next. Sorry, and K0, because they all belong to flip-flop number 0, and we're going to repeat the process for them. So in order for Q0 to transition from 0 to 1, we need the values of J and K to have a value equals to 1 and don't care. In the next row, we have Q0 transitioning from 1 to 0. So for that to happen, we need J and K to be don't care and 1. Next, Q0 is changing from 0 to 1. So for that to happen, J and K must be 1 and don't care. Finally, Q0 is transitioning from 1 to 0. For that to happen, we need J and K to be don't care and 1. So that completes the state table for experiment 3 of this lab. Now, with the help of the state table, the complete state table, we're going to derive K-maps for each values of J and K that we have in the table. We're going to start with the K-map for J1. We're going to copy the values of J1, so it will be 0, 1, don't care, don't care. Then we're going to group the ones that we have, which allows us to end up with J1 being equal to Q0. Next, we're going to create a K-map for K1. I'm going to fill it so that it has the values of K1. So don't care, 1, 0. Now we're going to group the ones together, which will result in K1 having the value equals to Q0 as well. Next is to do a K-map for J0. We're going to copy the values for J0. So we have 1, don't care, 1, don't care. We can group the entire K-map together. That will result in J1 having a value equals to 1. So 1 here means constant high or constant 1. So to connect that in Logician, we can simply connect a constant and assign it a value equals to 1. Next, we're going to do a K-map for K0. K0, when we fill its K-map, it's going to have the values don't care, 1, don't care, 1. Again, we can group the whole thing. which will result in K0 having a value equals to 1. So now knowing the Boolean expressions for each of J1, K1, J0, and K0 can simply translate the expression into a logic diagram, which will result in this logic diagram that uses two flip-flops. We can name them FF0, FF1. For FF0, the output is Q0, the inputs are J0 and K0, which are assigned a value equals to constant 1, as explained here. Notice that in the diagram, J1 and K1 are all equal to Q0, so we can short them together first and then connect them to Q0. And the output will have 2 bits, since this is a 2-bit incrementing counter. Notice that for a counter or for any binary numbers, here the number consists of more than 1 bit, so we need to know which one is the least significant bit. Notice that flip-flop number 0 outputs the least significant bit, so it outputs bit number 0 of the output. That's why I arranged the output bits so that the least significant bit is on the right-hand side. So this is LSB, the least significant bit. Here we're explaining some of the tips needed for the completion of this lab in Logisim. First is to place a constant or a clock. You can find these in the wiring group in Logisim. You can find the clock here, and then to place a constant, you can find it right under the clock. To change the constant value, you can simply change it from the settings of the constant to either 0 or 1. And also to allow the clock to run automatically, so it will change on its own without having to tick it manually. You can go to the simulate menu, and then the first thing to do is to make sure that the simulation enabled is ticked. Also make sure that the ticks enabled is also ticked here. Finally, to adjust the speed or the frequency of the clock, you can simply go to simulate, tick frequency, and then choose the desired frequency. For the purpose of this lab, I think 1 Hz is good enough, because it's slow enough so you can observe the change at the output, and it's fast enough so you don't waste much time waiting for the update. If the connection of the circuit is correct, at the output you should see the sequence 00, 01, 10, and then 11. Notice that this is the least significant bit, so it's output bit number 0, and this is output bit number 1. These are some practice exercises. If you're interested in doing them, you can take a screenshot or pause the video and then read them on your own. Thank you for watching, and good luck. If you have a question while watching this live, during a live session, you can always ask questions in the chat or using the mic. If you're watching this at another time, feel free to email me at aalatia@auk.edu.kw if you have any question.